Okay, in this video, basically we're going to talk about inverse functions, a very important thing in mathematics. Everything we do in algebra, we should be able to do forwards and backwards. So again, to have any function, we should also have an inverse function, a way to kind of work that backwards. And we just want to bring up a few things that inverse functions have in common. So note to self, first of all, up top, we've got an f of x function. We've got f of x equals 2x plus 6 up here. And notice we also have this f to the negative 1 of x. That's the symbol for inverse functions. So f to the negative 1 power. Now notice that's not x to the negative 1. You may remember that x to the negative 1 often means reciprocal function, right? It means we have a reciprocal like 1 over x. When that operation or that symbol is on a function, we call that the inverse function. So notice what happens when we talk about the tables. Let's do a table of values here real quick. So if f of x is 2x plus 6, I can plug in some numbers. Let's start with the easiest one. We'll start with 0 here. 2 times 0 plus 6 would just be 6. 2 times 2 plus 6 is 10. And 4 times 2 plus 6 would be 14. In that same way, we can plug in those negative numbers. 2 times negative 2 would be negative 4 plus 6 is 2. And negative 4 times 2 is negative 8, plus 6 is negative 2. Now, let's go to the inverse function over here. 1/2 times x minus 3. So negative 2 times 1/2 is negative 1, minus 3 would be negative 4. And notice what happened. When we plugged negative 4 into f of x, we got back negative 2. But when we plugged negative 2 into inverse f, right, or f inverse of x, we got back negative 4. Basically, our x values and our y values switched places. So the same thing is going to happen if I take 2 and plug it in. Well, 1/2 times 2 is 1, minus 3 is negative 2. And again, notice these 2 points sort of reverse spots. Negative 2, 2 just became 2, negative 2. All of the x values essentially are going to become our y values, which just makes sense that if I plug in 6 then, well, I got 6 back over here when I plugged in 0. I should get 0 back when I plug in 6. 6 times 1/2 would have been 3, minus 3 would have been 0. And again, the same thing goes for 10. The same thing goes for 14. You can verify those by plugging those into that f inverse function. But basically, you're switching your x's and your y's. In that case, it should make sense that the x-intercept and the y-intercept for f of x, so notice the red stuff down here at the bottom, the x-intercept, right, would have been if y was equal to 0. So if we put f of x being 0 over here, I would have subtracted negative 6 and divided by 2. So negative 6 divided by 2 should be a negative 3. My x-intercept for f of x should have been negative 3. And my y-intercept, very simply, it's y equals mx plus b. We're going to be 0, 6. Or if I had plotted that function over here at the right, 0, 6, and negative 3, 0. Notice we have that nice slope of 2 going. So up 2, right 1, up 2, right 1. Just working our way up the screen. And the same thing going back down the other direction, right? Getting us our line right here. Well, again, we're just going to switch x and y's to find our inverse function, which means that instead of an x-intercept, right, this is going to become our y-intercept. So you'll notice in that negative 3, right, in f inverse, negative 3 just became our new y-intercept. And in that same way, 0, 6 as a y-intercept just became 6, 0, switching x and y. And if we plotted the new function, again, we would have started at negative 3, right, our y-intercept, with a slope of 1/2. So up 1, right 2, up 1, right 2, basically traveling here. But again, same thing, down 1, left 2, down 1, left 2. And we would have ended up going right through that same point right there. And notice the point where those two graphs cross, well, that's the point, what, negative 6, negative 6. So it makes sense if we switch x and y, -6, -6 would have been on both graphs. Even if we switched the x's and y's, that would occur on both of them. In fact, a good relationship to remember, and kind of a very important one, if you actually graph the line y equals x, it's going to be that diagonal line. It's sort of that parent function of linear functions. Y equals x, right? Or f of x equals x. It's always going to be a perfect line of reflection for your inverse function. So again, we've got -6 right on the line. But again, -3, 0, and 0, -3, 0, 6, 6, 0, right? Being right there. And all of the other points, if you switch x and y, you've got an inverse function. Which helps us when it comes to how do you find an inverse function? What if we're not given the inverse function? What if we have to go find it? Well, the first thing to do is, again, f of x is a little tricky to work with. I'm going to call that y. But the first thing I'm going to do then is switch x and y. If I want to find an inverse function, I need my outputs to become my inputs, and all of my input values to become my output values. Then step 2, so step 1, right? Switch x and y. Step 2, solve for y. Basically, we don't like it equal to x. We want to get this thing back equal to f of x or back equal to y here. So I'm going to subtract 8. And then the easiest way to get rid of a half or get rid of that 0.5 is multiply by 2. So I'm going to say 2 times x minus 8. 2 times a half would have been 1, so that turns there. And now I'm going to take out that y. I'm going to convert it back. I'm going to call it f inverse of x would have been equal to, and while I'm at it, I'm going to go ahead and distribute. Let's call that 2x minus 16. Again, step 1, switch x and y. Step 2, solve for y. The function down at the bottom, it gets a little bit trickier. So I'm going to kind of walk you through that one. I'm going to go kind of quick here. But let's kind of imagine here, if I take out f of x and I call it y, but then I'm going to switch x and y, right? So again, if I call this y, but switch x and y, this gets a little tricky. I'm going to say x equals 2y plus 7 over y minus 6. Well, now how do you solve for y when there are 2 of them there? Well, the first thing I would do is not worry so much about the fact that there's 2 y's. That division always just makes things a little bit trickier. So I'm going to take what's in the denominator. I'm going to multiply it over to the other side. I'm going to say x times y minus 6 equals 2y plus 7. Then I'm going to go ahead and do something a little bit tricky. I'm going to multiply that x in there. I'm going to say that xy minus 6x equals 2y plus 7. Then while I'm at it, well, it's always easiest to solve for a variable if we can get those like variables on the same side. So let's go over here. I'm going to go ahead and add 6x to the other side, right? Basically causing that to be 6x plus 7. At the same time, I'm going to go ahead and subtract this 2y over here. I'm going to subtract 2y on both sides, so that now on this side it's xy minus 2y. Then we can get a little fancy if there's a y in both parts. Just like we distributed x in over here, I can factor out the y on this side, which gives me the opportunity then, if it's y times the quantity, well then why don't we go ahead and just divide by x minus 2. And finally then, instead of y, right, I'm going to take that back out. I'm going to call it f inverse of x is equal to, and again, what I get on the right there, 6x plus 7 over x minus 2. Again, had to get a little bit fancy, had to do a little bit of factoring there, but we still found a way to, again, switch x and y and solve for y. I think that's a good place to end this video. If you want another example, though, I'll make another video here soon. So feel free to look for part 2. Otherwise, if you have any questions for your teacher, that'd be a great thing to do. Any questions, always refer them to your teacher. Good luck, and have a great day.